In that case, we will amplify the input. Since beta is inversely proportional to the input resistance, if we now say that Rf is less than Rin, then this is no longer the amplification circuit. It won't amplify. We can say de-amplify the circuit. So these are the two scenarios that correspond to understanding the gain, how the gain plays an important role in the non-inverting amplifier. Let us now look at what will happen to this non-inverting input. For example, if we apply positive 5 volts at the input and we want to get a negative signal that will control a circuit or a sensor or a circuit parameters within a circuit. So we want to get, for example, minus 5 volts. So this negative voltage can be used in the electric circuit because there are no other circuit that can invert a signal except for the operational amplifier. So by looking at this, we can see that minus 5 and 5, they are the same. It can be a voltage follower circuit. However, we want to invert the output. So as a designer, you will have to design the gain of the signal. So for example, if you have 100 ohms and you also given 100 ohms, then you will have the feedback resistor having the value of 100 ohms divided by the 100 ohms as the input. Now you will have the gain of 1. By substituting into this equation, you now will get V out is equals to minus the beta times the V in. So minus 1 times 5 volts, you now get minus 5 volts. So the gain will now become the control mechanism, where depending on the gain, the response will be produced based on the system requirement. And this is similar to a voltage follower circuit having the inverted portion that makes it unique. So for the voltage follower, if we have these two value of the resistor which is the same, if we want to get the output which follows the input without inverting, we can just simply remove the resistor connected with the inverting and connect the input to the non-inverting portion. Then you will have it. And what will happen if you are given a requirement that you want a voltage to be greater? For example, we have the output which is minus 20 volts. So you need a 20 volts to control a component. So as a designer, you are now going to design the gain. So we simply, by looking at this in terms of the amplification, we know that we will choose the value of the feedback resistor to be greater than the input resistor. So 20 and 5, that means it has the output as 4 times greater than the input voltage. Therefore, we can design beta as, if we give, for example, 2 kilo ohm as the reference resistor or the feedback resistor, and what will be the Rin, we can just simply apply 500 ohms. So you can have 2000 divided by 500 ohms, you now should get 4. So this is the gain that will control the response of this amplifier. Therefore, substituting this gain into the equation, you now have V out is equals to minus beta times the V in, which is equivalent to minus 4 times 5. So you will have minus 20 volts at the output. So this represents the amplification, where we have the RF which is greater than the Rin. So RF value is greater than the resistance value of the input. In case of de-amplification, that means the value of the RF must be less than the value of the resistance connected to the inverting terminal. For example, if we have 5 volts at the input and we want to get minus 2.5 volts at the output, by looking at this, the output is half the input. So how can we design the gain? So beta now will become, for example, if we have 1000 ohms, we give RF 1000, what will be the Rin? So the Rin will now be 2000 ohms. So we will get beta as half. By substituting into the equation, V out now will be equals to minus beta times V in. We'll have minus half times 5, which will gives us minus 2.5 volts at the output. So this 2.5, negative 2.5 volts will be able to produce to be used in some of the component in an electrical circuit, and this is important. So by then you can be able to see what happens to the inverting part of the circuit and why we have the gain which correspond to either it will amplify the signal, de-amplify the signal, or become as a voltage follower as we discussed previously. Finally, we are going to look at the non-inverting. So non-inverting and inverting follows the same principle. So that means the non-inverting must always be connected to where? Must always be connected to the input to the non-inverting. And we have the output circuit connected like this. This circuit now forms the non-inverting amplifier. Let us now look at the mathematical representation of the non-inverting amplifier, and it is given as V out is equals to 1 plus Rf over R in multiplied by the V in. So when comparing it with the general equation of the system, we can determine beta as 1 plus Rf over the R in. With respect to the circuit, that means the voltage output will always be greater than or equal to the V in, and this can be seen in this equation. If Rf over R in is equivalent to 0, that means V out will be equals to V in. And what will happen if we increase or decrease the value? If Rf is greater than R in and Rf is less than R in. Previously we say in this case, this one is an amplifier. And this one will also be the amplifier. Comparing the portion, this one will be having large amplification, this one can have small amplification. So in this amplifier circuit, by looking at the mathematical representation of the signal, we can say both of these will act as the amplifier. Previously we look at we can de-amplify the signal of the inverting input. However, in this case, we always say the V out will always be greater or equal to V in. Although we increase the resistance of the input, that means the smaller and smaller this value becomes, it won't affect this value because it is added to the signal. So it will be greater or equal to V in. Now let us look at this example. However, if we want to apply a positive 5 volts at the input and we also want to get positive 5 volts at the output, what will happen to the circuit value, especially for the feedback resistor and the input resistor? Since it is plus 1, if it has any value, that means you will have a small variation in the output voltage. If you apply a 0 ohms and 0 ohms at this end, then you should be able to get beta is equals to 1 plus 0. By substituting into this equation, you now have V out is equals to 1 times 5. You should be able to get 5 volts. By applying any value of resistor in the R in or RF, will have a small variation in the output if you want to get a constant 5 volts output as a voltage follower circuit. So in that case, for the configuration for the voltage follower, we don't require the use of a resistance because it will still gives us a 0 volts and the beta will be 1 since it is a unity feedback without any form of resistance. But this is just to show you the difference between if we want to get the same voltage output as the same input. And let us see if we want to get now, for example, 10 volts to control a circuit component by applying the input voltage 5 volts. So how can we design this? So 10 is like 2 times the value of the input. So if you are to design, you will have to select these two value of the resistor, because we want to achieve the beta, which must be 2 times greater than the input. So we can have 1 plus the value of RF. That means if you want to obtain 1, that means 1 plus 1 will give you 2. That means Rin must be equivalent to RF. So for example, if we have 1000 ohms and 1000 ohms, this one is 1000 ohms, this one 1000 ohms, then this will becomes 2. So beta equals to not 2 but should be equivalent to 1. And now beta is equals to 2. By substituting into the equation, you now have the V out, which is equals to 2 times the V in. So you will get positive 10 volts at the output. What will happen if we increase maybe RF and decrease Rin? What will happen? To prove, let's say if RF is equals to 2000 ohms and Rin is equals to 1000 ohms. So what will happen to the gain? Beta now will becomes 1 plus 2000 over 1000, which will give us 1 plus 2. In that case, we can see that the beta is equivalent to 3. So this beta represents 3 times the input voltage. So if you have this configuration like this, you probably know that you want to get the output voltage that must be 15 volts. So by substituting into the equation, V out is equals to 3 times 5, which gives you 15 volts. So we can say by increasing the value of RF while keeping this one constant at 1000 and increasing RF, that means the magnitude of the voltage output will continue to increase. So what will happen now if we look at this example? We decrease the feedback resistor and increasing the input resistance in this circuit. So what I mean the input resistance, that means the input resistance to the inverting amplifier. So it will mostly act as a reference. So Rin is the input resistance to the inverting, which becomes the reference of the non-inverting input. Let us see, if we now say Rin is equals to 2000 ohms and RF is equals to 1000 ohms. In that case, we say Rin is greater than RF. So what will happen to the voltage output? We can calculate beta 1 plus 1000 over 2000 ohms. So equals to 1 plus the half, and it will be 1.5. Therefore, the V out will be equivalent to 1.5 times 5. What do we get? We will get 7.5 volts as the input. What will happen if we continue to increase the Rin while keeping this RF at a constant value? The value of the output will be closer and closer to 5, but it won't be going less than 5. Do you agree with me? Because of this value 1 here. So no matter if you increase this Rin, which is inversely proportional to 1 plus the RF, no matter if you increase to a larger value, the value of the output will be closer and closer to the input, but it won't go below 5 volts. That's why we say this one is also an amplifier circuit, and this is also an amplifier circuit, because it cannot decrease the value as what we have seen in the non-inverting portion of the signal. And I believe this example can help you understand the type of amplifier, and if you want to use it in a circuit, you can precisely choose what type of amplifier to be used. And then you can be able to calculate the gain to know what the amplitude of the output may correspond to the application that you are using. For example, controlling some appliance or controlling some circuit parameters, then you should be able to choose wisely. So with the simple mathematical representation and the explanation, I believe by now you can understand this equation. Maybe later on we'll do some simulation to see if we apply some varying signal at the input, what will happen to the output. If we apply AC at the input, what will happen to the output. So you can follow us for more videos, and we can be able to describe the differential amplifier and some advanced amplifier that can be used within an electrical circuit. So thank you again for watching. If you like our video, you can click the like button and subscribe and share with your friends if you find this video very interesting.